Welcome to Easy Learn. This is Introduction to Electronics Season 3 Episode 1 English, and I will give you the introduction about the terms used in this series very precisely. As you know, this is the episode 4, and let's talk about the topics that we are going to discuss today. Topics I will discuss in this episode is the nonlinear resistors, number 1. The second one is the p-n junction, and the last at the end I will give you some problems for your practice, very basic problems that you will solve them later on. Okay, first of all, the first topic I'm going to discuss right here is the nonlinear resistors. Nonlinear resistors are basically those devices that doesn't obey the Ohm's law. Similar principles can be applied to find potentials and currents in the circuits, but their mechanism may be a little bit different, but the equations used are same. For example, I'm giving you an example. A light globe has a resistance that varies with the potential applied. Heat is generated in the globe, and that alters the effective resistance at some set voltage. However, the resistance might not alter, and calculation of the current and potential can be made. Some devices change resistance with external conditions, and I will show you here. In simple terms, I can say that those elements whose VI curves are not straight but curves are called nonlinear resistors. Not straight curves, parabolic, maybe another type of curves. You will see in the upcoming slides. VI characteristics can be represented. What is VI characteristic? This is the same as this is basically graph of between the voltage and the current that we had already explained in the case of Ohm's law in our first lecture or second, I don't know. By the way, okay, the VI characteristics can be explained by the suitable equations. There are some examples: incandescent lamps, diodes, thermistors, and varistors. What is this varistors? Varistors are the device which basically a metal oxide material whose resistance decrease sharply. This is important here, sharply, very sharply, with the increase in the voltage. Whenever a voltage is increased a little bit, their resistance is decreased much, in a huge amount or a large number. For example, if 1 volt is increased, the resistance is decreased in maybe kilo ohms, or it depends upon the basically circuit and type of the resistors or for protection we use. For example, there are two types of zinc oxide based and silicon carbide varistors. If I'm using a zinc oxide based, its purpose is to protect the circuit for a medium or a small increase in the voltage. For example, if the battery is connected to a circuit and the voltage is maybe increased a little bit due to any fault or any type of any fault in the circuit or failure of a component, little bit or medium increase in the voltage is handled by the zinc oxide based, while a huge or a large amount of increase in the voltage is handled by the silicon carbide case. Silicon carbide example is this example. For example, if a circuit has a magnetic coils, then due to the magnetic effect, sometimes coil stores the charge, and if they release simultaneously the charge due to some maybe an error or sometimes any case, the silicon carbide can handle the increase in the voltage in a large number. And these is basically resistors are used for the protection. A resistor is a special resistor made of a carborundum crystals held together by a binder. Okay, this is the first case, that is zinc oxide based, and this is the silicon carbide. This is the same silicon carbide, and this from the diagram it's also you can see that this is a little bit heavier looks like, and this is the micro components, and these are used in the in the circuits for a lower protection, for a lower voltage cases or medium. Okay, first we are going to discuss temperature dependent resistor. Temperature dependent resistors are those whose resistance are changed when exposed to change in the temperature. A typical graph I will show you here. This is the graph with the temperature as shown. You can note it here. The scale is scale used in some technical specification in logarithm and are not maybe linear. It's not non-linear graph, so you must have to be take careful reading according to the graphs, because it's not non-linear. It's more, you have to be more careful when you are taking the readings of the non-linear. This is the symbol of the temperature dependent resistors. In short words, we can write TDRS, or thermistors are basically used for temperature dependent cases. So the most temperature dependents have negative temperature coefficient, as in the last slide. The resistance is decreased with the increase in the temperature. This is resistance have inversely proportional effect with the temperature. As temperature is increased and resistance is decreased, so this has a negative temperature coefficient. So most of the temperature dependent have a negative temperature coefficient called NTC, and also positive temperature coefficient is available, but they are rarely used. That's why I'm not going to discuss here. I'm using the temperature dependent or light dependent resistors that are NTC coefficient. NTC coefficients are used worldwide. Their resistance decrease with the increase in the temperature. This is the case here when I am using the temperature dependent resistor in the voltage divider circuits of the previous lecture. I replace the fixed resistor with the temperature dependent resistor. What happens when I am using this one? This is interesting. The temperature dependent, when I replace the temperature dependent the voltage circuit, the output voltage can depend upon the temperature now. Basically, when the temperature is low, here you can note that when the temperature is lower, the resistance of the temperature dependent resistor NTC is high. Okay, the output here, this V output is low. Okay, you can check out this from the equations from the previous lectures. While when the temperature is high, surrounding temperature is high, the resistance is lower and the output is high, V output is high. This is written in theoretically here. The circuit can be used to operate another device such as an air conditioner or heater. When the output is high, and a logic circuit can turn on air conditioner on and off an heater. A variable resistor is placed in the fixed resistor could allow some sort of temperature control when it is switched on and off. For example, when thermostats, we can set the temperature what we required in the air conditioner's case. Okay, light dependent resistor is the same like we had discussed the temperature dependent resistor. The difference is just they operate on the light, while their resistance in the previous case depends upon the temperature, while in this case they are sensitive to the light. Again, be careful with the logarithmic scale on either axis. This is the same graph, looks like light here, just light intensity. When light intensity is increased, the resistance is decreased. This is again NTC, and the resistance versus light intensity graph and the symbol for a light dependent resistor. Resistors may decrease from about 10 mega ohm, this is important, 10 mega ohm in the dark to a few hundred ohm in the strong light. So this is, you can see that, but it's not like a linear graph. Most importantly, first it's decreasing very steep graph, then it's maybe little bit looks like horizontal axis, straight along the horizontal axis. This is the symbol, and if we use in the same way in our voltage divider circuit, replace the fixed resistor with the LDR, light dependent resistor, and what we can what is the uses now, you can think about it. Some uses are explained here: night light sensors, street lights, etc. You can also think about others one in comments. You can also tell others what are your opinions. There are also devices in which the resistance varies with the outside effects such as magnetic effect, pressure and voltage. But again, why I am not using the other effects, I'm ignoring these effects. These are minor effects, number one. Second, I'm just concerned with the resistors case here, that depends upon the major effects, and this is the introduction series, not going in details. So this is the beyond the studies. Okay, PN junction. PN junction PN junction details is available in diodes and application series on this channel, while just a short description or just the touch is available here. Okay, semiconductors are used when we are going to discuss about the PN junction. Semiconductors are the base. They have a lot of the many useful properties available that are provided for the manufacture. All the chips in the mobile phones or integrated circuits are made up of the silicon. The major portion is silicon. If there is no silicon, it's difficult to make such a tiny or it's difficult complex chips as they are in now available. Okay, the best known of this is silicon. The most important is silicon. The most widely used element is silicon. You can see here in diagram silicon that it has atomic number 14 and 4 shell in the outermost or valence shell, 4 electrons available, and they are free electrons, and they can be used in the covalent bonding or with their neighboring atoms. We will see in the next slide. Okay, here important thing is, although other materials such as germanium and gallium arsenide are available, but we are used rare. Germanium is used, but in rare cases. The most important is silicon. Germanium has also the 4 electrons in the valence shell, but in his fourth shell, this is 1 2 3, this is third shell, you can see, but in germanium case it's a 4th shell. So this is another discussion that why germanium is not most widely used as silicon. I had also discussed in the diode and application series. You can also search on. This is the crystalline form of the this 4 outer electrons, as I already explained, shared with 4 neighboring atoms in the silicon crystal. This is, you can see that the 4 neighboring electrons. Here basically this diagram is for doping case. I added it for the doping. I will show you that this diagram for the neighboring atoms in the silicon crystal in the next slide. During manufacturing of the silicon chip, impurities are added. This is the impurity. This is in green. This is the impurity. These is 1 2 3 and 4 are the silicon atoms, and if we want to change the properties of this crystal, for example, this is a crystal of the silicon. If we want to change its property according to us, we want and we require, we add the impurity atoms, so this is called doping. This process is called doping. In this case, in this diagram, the phosphorus atom is used. Phosphorus has basically atomic number 15, so it has 1 more electron than the silicon. So one electron is used with this silicon, 1 is used with this, 1 is for this third, and 1 is used with the fourth one in this silicon case, while 1 electron is left free. So this is the electron, extra unbound electron. This electron is available free because it has 5 electron in its valence shell. So this cube, for example, let's say this cube overall has one extra electron and negative charge. So I know in the next slide the same thing is explained. If an atom with 5 outer shell electrons such as phosphorus, as I already explained, are added to this structure, the structure will have a free electron. This is important thing, free electron for every impurity atom. Here in the previous slide just one impurity is shown, but this is millions in a very small structure. So for just understanding, we had taken a cube and we just discussed with a single phosphorus atom. So this is a -1 charge. It depends upon the number. This is a phosphorus, it has 15 like 15 atomic number and a 5 outer electrons in the valence shell or last shell. These impurities produce free electrons as negative charge and carriers, as the materials is called n-type material. This is n-type material, this is n-type, n-dope. Because why we called it n-type? N is basically comes from the negative charge, because it's a negative, so n stands for negative. So here is the same thing. This is the one silicon atom. This brackets type things is basically a share of electrons. So here is the sharing of electron. It has 4 electron silicon. Each silicon atom has 4 electron in its valence shell. This silicon may use the covalent bonding with this one, 2. One is for its this is its valence electron, while it has also a valence electron. This is the sharing, and 2 electrons are used for the sharing. One is the both atoms share their single electron with each other, and this is another discussion how covalent bonds are formed and the details. Anyway, this is the another sharing. This is another thing. And 4, it's no stable. It has 4 covalent bonds. But if we add impurities of like in this case, previous case, we had added a phosphorus, and this is the phosphorus case, the red one. The one extra electron is available. Here you can see that this is the phosphorus first electron shared with the first silicon atom. This is the second electron shared with the second silicon, third and fourth. But extra electron is available, but no silicon atom is available here for the sharing, because each electron is well organized in the pattern. Okay, p-type doping. Here if we add an atom, impurities of an atom, dope with the impurities of an atom which has 3 valence electrons in its outermost shell. For example, you can see that this is the first electron, this is its second electron, busy with the second silicon atom, while this is the third electron of the blue. This is basically boron of the blue atom, while it has no here it is none. You can see that it's empty. This makes a missing electron, and we can say that this is a hole. So a hole is created, and we call it hole as a positive charge. This is basically not positive, but it is positive with respect to the n. So n with respect to electron, we can say it's a positivity. This if this electron comes here, then the hole goes there. If this electron moves here, then respectively this hole goes there for filling the gap of this electron. So hole can also move in this structure as like free electrons. So this is also a hole, and it can also move. So this is a p-type material. This is the same thing that I had already explained in the previous slide. Atom with the 3 outer shell electrons such as boron are added in the structure. The structure will have a missing electron for every impurity atom in the structure, and the same thing, the hole behaves as if it is a positive charge. This behaves as, okay, this is important, behaves as if it is a positive charge, but it's not actually the positive charge. Semiconductor material with the extra positive hole called the p-type material, while it's a second one. This is the same picture but in a different style for understanding this. Look at this. here it's a silicon, and there is no impurity atoms are added, while here in this B case, n-type material, the impurity atom is phosphorus and it has 5 electrons. First here it is shared with the first silicon atom, second is shared, third is shared with third one silicon, and fourth is shared with the fourth silicon, while there is no available no fifth electron is freely, and why it's not shared with the fifth silicon, because the pattern is like the 4 electrons is shared with each silicon, so there is no fifth one. Fifth is always free. So this is an n-type. P-type, there is a hole. You can see that boron, one is busy with first one, second one, and third silicon atom, while in this case silicon electron is available, but boron have no electron left in its valence shell, so it's a valence shell. It's a hole is created. There's the diodes. What are diodes? Diodes, when we join a p-type material with the n-type material, a p-n junction is formed. There is a barrier potential, but I'm not going in details, just saying that what is a p-n junction. p-n junction diode is, this is one side is p-type and one is n-type. Like when the potential difference is applied in such a way that the positive is connected with this p-type and n-type is connected with the negative, then we can say that the diode is forward bias, and if we reverse the polarity, it's a reverse bias. If it's a forward bias, it allows the currents to flow, while in the reverse, no current. Here you can see that no current flows, and if current flows, definitely our bulbs, etc., whatever the things will glow up, while in this case no current flows and no. This is the symbol that is used, and when the potential is applied across the p-n junction, the holes and electrons and holes travels in the opposite directions. The ideal case is this: when it is in forward bias, this is the forward bias, a current flow in one direction only and have a no voltage drop or energy loss. You can see here no energy in this axis along the voltage, so we can across it when forward bias. The graph of the current is here, you can see in this diagram. One more second, I'm just explaining one more thing right here. You can see that in the reverse bias case, this is the reverse bias case. In the left side there is ideal, because it's in ideal case, you can see that there is no current flows when it is in reverse bias. So this is a linear graph. Ohm's law applies to it very easily, but this is the actual cases, real or practical diode. The relationship between the current and the potential difference applied to cross it's not a linear. It goes to little bit slightly up to touches approximately 0.7, and it also depends upon our circuits. For example, sometimes our circuits have temperature or some other factors also affect these graph, but it's a nonlinear graph. Current, this is the little bit barrier due to barrier potential, this is, but I'm not going in details. This graph looks like the 0.7 volts across voltage axis, while in the reverse bias there is also a small current called the leakage current when the diode is reverse bias. In some application, the diode can be constructed to emit light when the forward bias. These light emitting diode LEDs are used in many electronic devices and will be explained later on, because this is not concerned right here. So this is called the characteristic curve this is the problems for you. You have to take care of these problems. For example, this is the diode is connected with the positive terminal of the battery, and here is a bulb maybe, or anything that will be glow. You have to tell that A is glow. For example, this I'm explaining this A diagram. The positive terminal is connected with the positive one, then it's a forward bias, also. This positive comes out here, so this diode and this diode is forward bias. It means A, whatever the A is, maybe it's a bulb, it will be glow. If the second case, the B will not glow because it's a reverse bias. The positive terminal is connected to the N type, so it's a reverse bias, and this is the ideal cases. So we can say that it's no current flows through the B and it will not glow, while there is no diode here and an additional diode, so this diode is also already forward biased, so C also glow. You have to tell about these other things. Answers I will show on the Facebook page, and this is also other things. This is a tricky question a little bit, but you have to answer it okay at the end termination. Next time I'm from the episode 5, I'm just moving towards the capacitor sides, as resistors is just already explained much more, and no need more to discuss the resistors. So going towards the capacitor side, introduction of the power supplies, the multimeter, cathode ray oscilloscope will be discussed in the next episode 5. If you like this, then share this to spread the knowledge in easiest way. Watch, learn, glow, and see you next time.